Advanced Placement Chemistry, welcome back. This is the first of a series of review lessons to get you ready for the AP exam, which will be held on June the 10th. That's what is tentatively scheduled, and that should be the date on which we hold it. That gives us about 2 months to get ready for the exam from today, and this is being recorded on April the 3rd right now. Okay, so we're going to go ahead and this is a 4-part lesson. The idea is to get through basically one lesson of review per week for the next 3 weeks. And this is going to be on thermodynamics. It's a subject we just touched on at the very end of class. And it also incorporates thermochemistry, which is something we did much earlier in the class. So thermochemistry, thermodynamics are related subjects. Thermodynamics extends thermochemistry. So the first 2 lessons, part 1 and part 2 here, are going to be on thermochemistry, which we did back in October, November, right around that time frame. And then the last 2 lessons of this review are going to be in thermodynamics, which we touched on a little bit at the end of class, as I said, but not that thoroughly. So let's go ahead and get started on this. Hopefully some of this sparks your memory and you'll remember some of what we did on this. So a quick review of thermochemistry. So thermochemistry is the study of heat energy taken into or released by a chemical reaction. In thermodynamics or thermochemistry, we divide a chemical reaction into the system, where the reaction takes place, and the surroundings, which is everything outside of the system. And if you put those 2 together, that covers everything. So the system plus the surroundings is called the universe. The change in energy equals work done on the system plus heat absorbed by the system. Now that's if work is positive and if heat is positive. The work will be done against the system, not the system doing work on some outside force, but rather the work being done against the system, and heat absorbed into the system are positive W and positive Q. So there's the formula. Change in energy equals Q, heat, plus W. Work requires movement against a force. If the only force against a chemical reaction is the pressure of the atmosphere, then no work is done. Really, in chemistry, we want to focus on the energy of the reaction. So we want to simplify this process, and we do that by eliminating work. If no work is done, then all of the energy is in the form of heat. Work is really a subject for physics, where things move. If you remember taking physics, we talked about work equals force times distance. But if there's no force being put on the chemical reaction, then all of the energy going in or coming out will be in the form of heat, which we can measure without complicating the situation with work. So this means that at constant atmospheric pressure, the equation reduces to delta E, change in energy, equals Q, heat, either heat in or heat out. The heat taken in or released by a chemical system at constant pressure is called change in enthalpy, and it's represented by the symbol delta H. So very simply put, delta H, change in enthalpy, means heat, Q. Sometimes Q is used, sometimes delta H is used, but they both mean the same thing. It's the heat going into or coming out of a chemical reaction. For the rest of this course, heat entering or leaving a chemical reaction will be represented by delta H and represents the change in energy, delta E, of the reaction. So if we know the heat going into a reaction or coming out, we know the change in energy, and that energy comes from the chemical reaction. So therefore, we can know how much energy is being produced by a chemical reaction by measuring the heat. So positive delta H represents heat entering a chemical reaction. Negative delta H represents heat exiting a chemical reaction. For the rest of this course, heat entering or leaving a chemical reaction will be represented by delta H. An endothermic process is when heat enters the reaction and is shown with a positive value plus delta H. An exothermic process is when heat leaves the reaction and is shown as a negative value, negative delta H. Just remember that money into your bank account is positive, and when money is withdrawn from your bank account, it's negative. So heat in is positive, heat out is negative. The heat leaving the reaction system equals the heat entering the surroundings. So remember, our universe consists only of two things: the system where the chemical reaction is taking place, and everything outside, which is called the surroundings. So if heat leaves the system, leaves the chemical reaction, then it goes into the surroundings. So the amount of heat leaving the system is equal but opposite sign to the heat entering the surroundings. It could also be the reverse. Heat leaving the surroundings and going into the chemical reaction would be negative Q surroundings equals positive Q for the system. There are many kinds of energy. Mechanical, throwing a ball would be an example of mechanical energy. Electromagnetic, sound, light, heat, and others. You study all of these in physics. For our purposes, the only kind of energy involved in a chemical reaction is heat energy. If we can measure the heat absorbed or released in a chemical reaction, we can know how much energy can be gained from that reaction. And that chemical energy could be used for other things. It could be used for powering a machine, such as a car. It could be used for producing light. It could be used. It could be changed into other forms of energy, transformed into other forms of energy. So there are four methods by which we can measure the heat either going out of or coming into a reaction. The most important, the one you really should know, I can't say it's the most important, but it's one that they will definitely ask you on the AP exam, is called calorimetry. So in calorimetry, heat is released by reaction into the water. It could also be absorbed by the reaction from the water, but we're going to take the most obvious case where it's released by the reaction into the water. Now, there's no device to measure heat, but there is a device to measure temperature, and you know what that's called. It's called a thermometer. So what happens to the water is the temperature is measured, and then using an equation that relates heat, Q, to change in temperature, delta T, we can determine, based on the temperature change, how much heat came out into the water. So Q equals mc delta T is used to determine the heat energy. And we'll talk about what M and C mean in just a moment. So there's two types of calorimetry: constant pressure calorimetry, which is often called coffee cup calorimetry, and literally in a classroom we would perform this kind of calorimetry in a styrofoam coffee cup. And then there's constant volume calorimetry called bomb calorimetry. Unfortunately, we don't have the type of equipment required to do that, but it is what it's described. It's something that could literally explode. So it's in a sealed chamber, a sealed container inside the calorimeter, and when that explosion goes off, it releases heat. That explosion could be from gasoline, such as gasoline that fuels a car. Or it could be from a food product. You burn a food product and you can determine how many calories are in that food product. Next is Hess's law. And the unknown enthalpy of a chemical reaction, you can determine that by combining other reactions with known enthalpies. Again, we'll review this concept. 3 is enthalpy of formation. The enthalpy of a compound is computed by using the enthalpy of the elements from which it is made using the equation. So in other words, you use the enthalpy of formation of each of the elements in that reaction. Again, when we see an example, we'll see examples of this. And 4, bond energies. Energy released by each bond in the products minus energy absorbed to break each bond in the reactants. So those are the 4 methods. Calorimetry, there's 2 different types, but that's basically one method of determining the energy coming out of a chemical reaction or going into a chemical reaction. So that's the purpose of all of this, is using heat energy, you can determine how much energy is in that chemical reaction or comes out or goes into that chemical reaction. That's the whole purpose of thermochemistry. So let's start with calorimetry. Calorimetry is a process where the heat of a chemical reaction is released into a container of water. The temperature change in the water can be used to calculate the amount of heat. Again, we don't have a device that can measure heat. but we do have a device that can measure temperature called a thermometer. Now let's review what's the difference. Heat is an actual transfer of energy from a higher temperature to a lower temperature. So if you have an object of higher temperature and an object of lower temperature and they're in contact with each other, the energy will flow from the higher temperature object to the lower temperature object. That's what happens when you put a pan of water on the stove. The heat flows from the stove into the pan. All right, so that's a heat transfer. That's a transfer of heat energy from a higher temperature to a lower temperature. Temperature itself is the kinetic energy, the motion energy of the molecules of a particular object. So temperature exists within an object. It's the kinetic energy of the molecules or atoms that make up an object. Now let's say you had a piece of iron. You may say, well, the molecules or the iron atoms don't move because they're stuck in solid iron. But they actually do. They wiggle. And they can wiggle hard enough that they put out heat energy. So temperature exists within an object. Heat is the transfer of energy from an object of higher kinetic energy to an object of lower kinetic energy, and that flow is called heat. So that's the difference between temperature and heat. Temperature exists within an object. Heat is a transfer of energy between two objects of different temperatures. So this is the amount of energy released or absorbed by a chemical reaction. So constant pressure calorimetry, also called coffee cup calorimetry, is carried out in a container open to the atmosphere. This means that the process always maintains the pressure of the atmosphere of the room. So if it's carried out at the atmospheric pressure, it's not causing anything to move. It's not causing any work to be done. It's free to, the pressure will always stay the same at the pressure of the atmosphere of the room. So let's see an example here. So constant pressure calorimetry consists of these steps. We will dissolve a package of sodium hydroxide, NaOH, in the water. So there you see NaOH. It's an ionic compound, and it will dissolve in water. And as it does, it's going to release heat. So step 1, dissolve NaOH, that's sodium hydroxide, in water by the reaction NaOH aqueous. That simply means the NaOH is mixing with the water. Aqueous is a solution, mixture of two things. Produces Na, that's sodium ions, in aqueous solution, that is in water solution. And OH, that's hydroxide ions, in aqueous solution. In this reaction, the system. So now we got to define what is the system and what is the surroundings. The system is the reaction of the NaOH dissolving in water is the system. This is what we are studying. So it's not the NaOH itself. It's not the mass of the NaOH. It's the reaction. It's the breaking apart of those Na and OH ions. The surroundings is the solution. So what that means is it's not just the water. It's the water plus those Na ions and OH ions mixed in. The reason is because the surroundings are going to absorb the heat from this chemical reaction. And the surroundings are not just the water. It's also the mass of the Na and OH ions. They're going to absorb some of the heat as well. So the heat is released from the chemical bonds breaking. That's the system, is the chemical reaction, and the surroundings is the actual water and the sodium and the hydroxide ions all mixed together. That's the solution and that's the surroundings. So constant pressure calorimetry consists of these steps. 2, this chemical reaction releases heat, Q, into the water. So you see the Q coming out of the NaOH. And in actuality, that NaOH is distributed all throughout the water there. It's not in one place, but we're just doing that to visualize the concept. We're just saying that it's all staying together in one clump in the middle, but it's really spread out evenly throughout the water. But we do not have a way to directly measure heat, so that's a key point to remember. We don't have a heat meter that can measure heat. So what we need to do is measure it indirectly. So step 3, the heat Q released by the chemical reaction of NaOH, the system, all goes into the solution, the surroundings. So you see how the water got hotter there, right? When the heat came out into the water. The system, this means that the system the heat is negative because it is exiting exothermic. So it's a positive Q for the surroundings because heat is coming into the surroundings, and it's an equal and opposite negative Q for the system, which is the chemical reaction. So the amount of heat that came out of that chemical reaction is the same number value as the heat that went into the surroundings, into the water solution. It's just the sign is opposite. It's positive for the surroundings because it's going in. It's negative for the system because it's going out. So the surroundings, all heat leaving the system goes into the surroundings. This means that negative Q of the system equals positive Q of the surroundings. Also, no heat escapes from the container. So the container, that cylinder there, none is getting out or coming in. So step 4, heat entering the water spreads out uniformly, evenly. This causes an increase in the temperature of the water, or really of the solution. The amount of heat cannot be measured directly. However, heat can be computed from the temperature change of the surroundings. So the heat that came out into the surroundings is going to equal, and here's the key formula. It equals the mass of the surroundings times the specific heat of the surroundings. But in this case, the specific heat is just that of water. Specific heat is a characteristic of a substance, and it basically means how easily does a substance take in or give off heat based on a change in temperature. Water has a very high specific heat. It can absorb a lot of heat without its temperature going up. It can give off a lot of heat without its temperature going down. So the way to think of that is, imagine you're outside at Hoover at 7 o'clock in the morning on a sunny day, and you have a cup of water out there, and you stick your finger in the cup of water, and it feels kind of cool. It's not really cold, but it's cool. Then you go over to a metal bar, a rail of some sort, and you touch it. It's really cold at 7 o'clock in the morning. Then you come back at 2 in the afternoon. You leave the cup of water out, and you come back at 2 o'clock, and you stick your finger, and this is a hot day, let's say. You stick your finger in the water. The water feels warmer, but it's not hot. It's not boiling. You can stick your finger in without burning your finger. You go touch the metal railing, though, it's going to be really hot. It'll burn your fingers if you keep it on too long. So why does this happen? Because water was able to take in a lot of heat without changing its temperature very much. That's why you could stick your finger in at 2 o'clock and it didn't burn your finger. On the other hand, something with a low specific heat, such as an iron bar, iron rail, will change its temperature quite a bit when it takes in the same amount of heat. After all, both the water and the rail took in the same amount of heat. The sun was hitting them equally. But the railing, its temperature really went up when the sun hit it all day long, whereas the water not so much. So when something has a high specific heat, its temperature won't change very much if you add heat, nor will it go down very much if you take out heat. Where something with a low specific heat, such as iron or aluminum, if you put heat into that, the same amount of heat, its temperature will go way up and it will be hot. You won't be able to touch it. So specific heat is a characteristic of each substance. Each substance has its own specific heat. And then finally, the delta T is the change in temperature. So this equation relates the heat to which we can't measure directly, to the change in temperature, which we use a thermometer. We can measure change in temperature. So we're going to watch there as the temperature is going to go up as the heat comes out. So that just symbolizes the temperature going up. So step 5. So this is what we know about the reaction. All the heat entering the solution, that's the surroundings, that's the Na and OH ions and the water mixed together, is equal and opposite to the heat leaving the system. That's the reaction. Those are the chemical bonds that are holding those Na and OH together before they were broken. All of the energy exiting the system is in the form of heat. Conclusion, the heat computed represents the total energy change of this reaction. And note, as I said earlier, in an actual calorimetry experiment, the NaOH would be spread throughout the solution, not in a single central location as it appears in this diagram. So let's see an actual example with actual numbers. So dissolving 6 grams of calcium chloride in 300 milliliters of water causes the temperature of the solution to increase by 3.43 degrees centigrade. Assuming the specific heat of the solution is 4.18 joules per gram centigrade, that's a number you almost should memorize. It is the specific heat of water, but since the majority of the solution is water, we can just assume it's the specific heat of the solution as well. Sometimes you can make those assumptions and simplify it. So that is the specific heat of water. And assuming the calorimeter absorbs no significant amount of heat, determine the delta H for the reaction. And once we know the delta H from the reaction, we will know how much energy was in the chemical bonds of the calcium chloride. So there's the chemical reaction, similar to the sodium hydroxide. Ca plus Cl2 will give you a Ca2 plus ion and 2 Cl1 minus ions. So you get those off your periodic table of charged ions. Now there's an important relationship to understand for water here, is that 1 milliliter of water equals 1 gram of water. The metric system is really designed around the properties of water. So when you think of what a milliliter is, it's amount of volume, it's how much space the water takes up. And 1 gram is the weight of the water, it's the mass of the water. And when you think about it, there's no reason why those two things should be related. How much space something takes up with its mass. But they have actually defined that 1 gram of water will be 1 milliliter of water, or actually the other way around. 1 milliliter of water will equal 1 gram of water. That's only for water. That's not true for any other substance. Okay, so we can use that in this problem. Okay, so system. The reaction of the calcium chloride dissolving in water is the system. This is what we're studying. It's not the calcium chloride itself. It's the bonds that are holding it together that are releasing energy as the calcium chloride dissolves in water. That's the system. The surroundings, the solution is the surroundings. This is both the mass of the water and the mass of the calcium chloride. So let's go ahead, and all of the energy given off in the reaction, the system, enters the water, the surroundings, as heat. So that's positive Q for the surroundings. The heat went into the surroundings, so for the surroundings it's positive Q. For the system, that same amount of heat energy is a negative Q because it's leaving the system. It's leaving that chemical reaction. So this is the same amount of heat that is exiting the system reaction into the surroundings, negative Q. The surroundings is the mass of the water plus the CaCl2. So negative Q of the system equals positive Q of the surroundings. So the amount of heat cannot be measured directly. However, heat can be computed from the temperature change. So again, we have the temperature going up. So Q of the surroundings equals mc delta T, and we have those numbers up above. So this is how, be sure you understand how these numbers are applied here. So the mass is the water, which we said 1 milliliter of water equals 1 gram. So 300 milliliters is 300 grams of water. Plus you have to add the mass of the calcium chloride. That's part of the surroundings as well. So it's 300 plus 6 is 306 grams for the surroundings. Then the specific heat of water is 4.18 joules per gram degree centigrade. And then we said that the temperature change in the problem was given as 3.43 degrees centigrade. And now you got to be careful that joules is the unit of measure here because the specific heat is in joules. So you're getting an answer in joules. So if you look at the units, they're going to cancel. Centigrade cancels with centigrade, grams cancels with grams, and you end up with 4,387 joules of heat were released into the surroundings, are absorbed by the surroundings. So the surroundings is the mass of the water and the CaCl2 combined. Okay, so if the surroundings absorbed 4,387 joules, then the system must have released 4,387 joules. That's the only place that heat could have come from. The energy Q of the system comes from the 6 grams of CaCl2, not from the water. So be clear on that point. The energy all went out into the mass of the surroundings, which is the water plus the CaCl ions broken up. But where did that energy come from? It didn't come from the water at all. It only came from the 6 grams of the CaCl2. So if you want to figure out how much heat you're getting out of CaCl, you don't include the weight of the water. The water is just kind of a holder for the heat. Think of it that way. It just holds the heat. It doesn't produce the heat. So to find the molar heat of reaction, what that means is how much heat energy, how much energy are you getting for 1 mole of this substance of CaCl2? You calculate the number of moles of CaCl2 in 6 grams. Again, don't include the mass of the water because that's not what's releasing the heat. Only the CaCl2 is releasing the heat. So we just do a molar mass conversion. So for CaCl2, again, you can compute that from your periodic table, 110.98. You add 2 Cl's plus 1 Ca from your periodic table from the mass numbers at the bottom, and or the molar masses at the bottom of each of those elements, and you get 110.98. So now you do the conversion. The Q of the system for a mole is negative 4387 joules for every 6 grams. So that's how much heat, 4387 has how much heat you got out of 6 grams of CaCl2. Now we multiply by 110.98 grams for every 1 mole. You can see that grams is going to cancel out, and you're going to end up with joules per mole, and in this case that's 81,144 joules per mole of energy that you're going to get out of CaCl. Or oftentimes it's expressed in kilojoules. I didn't do the conversion here on screen, but you divide 81,144 by 1,000 kilojoules per joule, 1,000 joules per kilojoule, and what you get is 81.1. You just move the decimal over 3 places if you like to think of it that way. So that's how you determine how much energy you can get out of CaCl2 dissolving in water. Now let's talk briefly, I'm not going to do a whole problem, but this is constant volume calorimetry or bomb calorimetry. So constant volume calorimetry, also called bomb calorimetry, involves the combustion of a material in a container, it should be. The process is known as bomb calorimetry because it literally involves the combustion or explosion of a material. As I say, you could be burning a food product, you could be lighting gasoline on fire or some kind of combustible hydrocarbon that literally will explode. So that's why it's called bomb calorimetry. So this is often a hydrocarbon such as methane. So you see over there in the container there's CH4, that's methane. And it releases heat the same way. The only difference is, a couple differences. One is it actually is in a container. You can't have gasoline or methane inside of water. You can't just drop it into water. It has to be inside of a container. But what that container will do is allow all of the heat inside the small container where the CH4 is to get out into the water. So it actually is a physically separate chamber in this case. So as a result, the heat released is greater than the coffee cup calorimetry. Yeah, that's pretty much usually true with bomb calorimetry. So bomb calorimetry differs from coffee cup calorimetry in the following 2 ways. 1, the reaction takes place in a small container within the larger container, not in the water as does the coffee cup calorimetry. And 2, the surroundings are the entire calorimeter, not just the solution. It's not just the water. The specific heat of the calorimeter must be measured in a separate experiment. So in other words, the heat that comes out of that little chamber inside where CH4 is, it's not just going to be absorbed by the water, it's also going to be absorbed by the calorimeter, that is the big container there. Some of it is going to go in there. So you need to know what the specific heat, not just of the water is, but of the entire calorimeter. And it's just a difference between bomb calorimetry and coffee cup calorimetry. Alright, so that takes care of the first lesson. It came in at about 30 minutes. Now I have a problem set. It's got a number of problems. What I would do is try to go through, watch the video of the problem answers, try to think about them a little bit. Don't just watch them like you're watching a movie. Try to think about the problem, see if you can answer them yourself. And if you can't, then watch my solution. I'll give you the solution to those. And by the end of this coming week, you'll be able to get through both thermochemistry and thermodynamics. As I said, we did cover thermochemistry. We didn't cover all of thermodynamics. So it's what I consider one of the new subjects that we're going to cover before the AT exam. All right, I'm going to make myself available. I'll let you know when those hours are going to be so that you can work with me or ask me questions. And if you have any concerns about this, just please share them with me. But we've got 2 months to get ready for this test, so even though we've lost some time, it's not hopeless. In fact, you still have a very good chance of doing well on the test if you apply yourself. Okay, so I'll see you on the next video.